Next effect or next phenomenon that Fluent models is the cavitation effect. Cavitation is basically formation and immediate implosion of cavities in a liquid. That is, when small liquid-free zones or bubbles are formed which are a consequence of forces acting upon the liquid. As you can see in this figure, these are the small bubbles which implode and such type of cavities are formed in this liquid flow around the turbine. The second figure shows damage to the blades due to the formation of cavities or the cavitation effect. The third figure is also an example of damage to the device due to the formation of cavities. So cavitation is mainly an adverse effect which damages the blades and turbines. Cavitation occurs because liquid is subjected to rapid changes of pressure. These changes cause the formation of cavities where pressure is low. During this process, a liquid at constant temperature is usually subjected to decreasing pressure. Sometimes this decreasing pressure may go below the saturated vapor pressure. Because of this, there is rupturing of the liquid by the decrease of pressure at constant temperature. This rupturing of the liquid is called as cavitation. The liquid also contains bubbles of non-condensable gases which under decreasing pressure may grow and form cavities. So basically, whenever there is cavitation, very large and steep density variations happen in low pressure cavitation region. So modeling cavitation or the onset of cavitation is extremely important in order to study the behavior of liquid flow around turbines. It is extremely important to capture the cavitation effect in order to study or design blades of turbines so that cavitation does not adversely affect the turbine performance. There are three cavitation models available in Fluent. First is single état model. This includes cavitation effects in two-phase flows when the mixture model is used. This is a full complete cavitation model, that is, it models cavitation considering all the factors. The next is the Zwart-Gerber-Bellamri model. This can be used in both Eulerian as well as mixture multiphase models. Third is the Schneer and Saur model. This is the default model. This model can also be used along with both the mixture and the Eulerian multiphase models. While modeling cavitation within Fluent, there are some assumptions that are considered while building up the models for cavitation. We will discuss those assumptions in this slide. Now, the system under consideration in order to study cavitation must consist of a liquid and a vapor phase. This is the basic assumption. That is, the problem should contain a liquid phase and a vapor phase. There is mass transfer between the vapor phase and liquid phase, and this mass transfer should be modeled or it is assumed to take place. Both bubble formation, that is evaporation, and bubble collapse, that is condensation, are taken into account. Both the effects are modeled. Fluent defines a positive mass transfer from liquid to vapor. This is the sign convention that is used, that is, whenever there is a mass transfer from liquid to vapor, it is considered as positive, and vice versa. The cavitation models, that is, all the cavitation models within Fluent are based on Rayleigh-Placid equations describing the growth of single vapor bubble in a liquid. The singleton model that we just discussed in the earlier slide. In this particular model, non-condensable gases are introduced into the system. The mass fraction of the non-condensable gases is assumed to be a known constant. That is, we need to provide the non-condensable gas mass fraction which is introduced into the system when we use a singleton model. So these are some of the basic assumptions or basic facts that we must know before we study or model cavitation in Fluent. The input material properties used in the cavitation model can be constant or function of temperature or user defined. So we can change the input material properties as required. So these are basically the assumptions or known facts that we must understand or know before we start modeling cavitation within Fluent. As cavitation is a very complex phenomenon, there are some limitations when it comes to modeling cavitation. We will see one by one these limitations in this particular slide. none of the cavitation models work along with VOF. This is mainly because the surface tracking schemes of VOF are incompatible with the interpenetrating continua assumption of cavitation models. That is, when we consider cavitation or when we model cavitation, there is mass transfer or penetration of one medium into other. This is basic violation of the VOF principle of surface tracking. So, we cannot model or cannot use VOF model along with cavitation models. We can study or model only one single cavitation process. That is, we cannot model multiple cavitation processes within a single problem when we are using the cavitation model. Only one single phenomenon of cavitation can be modeled. The singleton model, that is one type of cavitation model, it requires primary phase to be liquid and secondary phase to be vapor. And this model can only be used with the mixture model. That whenever we use the singleton model, we have to activate the mixture model and we have to assign the primary phase as liquid and the secondary phase as vapor. This cannot be changed or modified. Singleton model does not work with the Eulerian model, it works only with the mixture model. It is also not compatible with the LES turbulence model. The Schwarzschild-Bellambi and the Schneer and Saur model do not take the effect of non-condensable gases into account. So these are some of the limitations when it comes to modeling cavitation within fluent, and we have to consider them whenever we go on solving for a cavitation model, a cavitation problem. Next we will see how to set up a cavitation model and how to give user inputs for activating the cavitation model.